All right, let's start. Welcome to these community talks. We are very happy to see you all. This presentation is titled Remote Sensing for Urban and Rural Development and Resilience in South Africa. We would like to welcome the speakers, Liesel Vermeulen and Tishilti Manyanya, both PhD students from KU Leuven, and also Bruno Verbist, project lead also from the KU Leuven. Before starting, let's allow me to make 3 practical announcements. So throughout the presentation, you can raise your questions in the chat. We will make sure to discuss them during the Q&A. During the presentation, please mute yourself. However, during the Q&A, you can unmute yourself, put your cameras on, and address your questions directly to the presenters. And finally, be aware that this community talk is being recorded. We like to share it and publish it on our website afterwards, so everyone who wants to watch it or rewatch it can do so. Voilà, so without further ado, let's dig in. We hope you enjoy this community talk.
Hello, my name is Liesel Vermeulen, and I'll be starting the community talk with my focusing on my PhD research. So I hope you can all see my presentation. Yes. Okay. So my research focuses on climate change, local anthropogenic degradation, and how this affects rural ecosystem stability. So understanding the ecosystem stability in Africa is a fundamental challenge in ecology, as they're dependent on complex interactions between very context-dependent variables. So these variables include multiple change drivers, such as climate change and human activities, natural disturbance cycles, for example, fire or herbivory, as well as local ecosystem characteristics, such as the soil, the terrain, and the vegetation type at each location. So assessing ecosystem stability basically involves disentangling how all these different variables interact and how this influences how the ecosystem responds. So in other words, how stable it is. So I focused on two main ecosystems. Firstly, the savanna, and secondly, the fynbos. Both are classified as dryland ecosystems and play a very important environmental, ecological, and socio-economic role in South Africa. This is important to ensure that it fits within the climate adaptive goals of the Resider project. And both of these are investigated using a combination of remote sensing techniques and fieldwork at selected local sites. So let's first focus on the savanna, more specifically abrupt shifts in the arid African savanna. So what are these abrupt shifts? When I talk about abrupt shifts, I talk about an ecosystem that's experiencing a sudden change in a way that it's functioning. And in savannas, that usually means a sudden increase or decrease in woody vegetation. So this can look like a sudden increase, so a woody encroachment in the savanna, or it can look like a decrease in woody vegetation. So either shifting to a grassland or, in worst case scenario, a desertification. So we want to answer 3 questions around these abrupt shifts. Firstly, where are they? Secondly, why are they there? And thirdly, what do they look like? So to answer the first question, where are they? I used a combination of remote sensing and time series analysis. And this essentially involved measuring vegetation greenness using satellite imagery through time, giving us a time series of how the vegetation is changing throughout time. So this is basically this gray line that you see here in the graph. Then we apply a breakpoint detection algorithm to pinpoint where there might have been very abrupt changes in how this vegetation is fluctuating. And this is the dark blue line that you see here. And where we see a change, this would then represent an abrupt shift in how the ecosystem is functioning. And if we do this for the whole study area, for every location, we can map it for the entire savanna. So this is essentially the output of that mapping. So we have here in dark gray the whole of South Africa, and light gray the savanna biome in South Africa, and then each of these colored blocks represent where an abrupt shift had occurred, and then the color represent what year it occurred. So the first thing we can see already is that we have 2 clusters. So the first cluster is much more dispersed spatially, so it's spread out, and also in time. So you can see there are a lot of different colors which represent a lot of different years that these shifts occurred. But then when we looked at the second cluster, it's much more uniform. It's very centrally located in one area, and all of the shifts occurred at the same time period. So we'll come back a bit later to zoom into this cluster B, why this happened here. But before we do that, we first want to answer the question, why are they here? Why did these abrupt shifts occur in these specific locations? So to answer this question, we used a technique called survival analysis, and this is usually used in medicine to essentially try and figure out what covariates drive the death of patients. In our case, the patients are the ecosystem, and then the death is when a shift in the ecosystem functioning occurs. So where these abrupt shifts have occurred. And then the drivers that we are looking at is climate legacy. So essentially past drought and fire event, past drought and extreme rainfall events. And then we also look at ecosystem characteristics. So what type of soil, terrain, and vegetation type drive these deaths essentially. So what we found with this analysis is that flatter slopes, colder temperatures during the summer season, and sandier soils lead to savanna landscapes being more prone to these abrupt shifts. And here you can see the percentage by how much it increases the probability of an abrupt shift occurring at that location. But most importantly, we find that a history of severe rainfall events drive these major abrupt shifts the most, by more than 200% more than the other characteristics. This is quite interesting and unexpected, as droughts are typically seen as the biggest threat in arid ecosystems in Africa. So it's important to note that we should be looking at these when doing climate modeling as well. We should also be looking at how severely wet our climate variability is. Then this brings us to the last question. What do these changes look like on the ground? So here we combine remote sensing and field data. And this essentially involved some field work. So if I go back to the cluster that I highlighted before, so cluster B, that's very uniform, and they all happen at the same time, we zoom in a bit here. So this is the Kruger National Park in South Africa. It's a very famous conservation park consisting of semi-arid to arid savannas. And basically what we did is we went and did some field surveys to try and figure out what is happening in terms of biodiversity within these blocks. So in the red blocks, we have our abrupt shifts, and then the purple dots is where we conducted field surveys. And we conducted field surveys in both areas that were unchanged, so did not experience an abrupt shift, as well as areas that we detected with our remote sensing have experienced these abrupt shifts. And then we compared them in terms of species diversity to see how are these shifts actually affecting the local ecology. And what we found was that in these changed areas, there was a loss of large trees, so trees that are larger than 6 meters, but at the same time, they have experienced an increase in shrubby vegetation. So woody vegetation that's smaller than 5 meters. If we look at this visually, this means that the landscape has been shifting from a more open, balanced savanna, as we see here, to a more dense shrub encroached landscape. So essentially shrub encroachment has occurred. And this is often associated with ecosystem degradation when it comes to savannas. And based on these findings, we could then follow this up with an analysis for a data-driven management plan. So in this case, we want to preserve large trees, but we want to clear too densely shrubbed areas. So essentially, we want to compare tree versus shrub diversity. So how we did that is we used our map of remotely sensed shifts, so these blocks, and then we colored them according to shrub diversity and tree diversity that we measured with our field data. And this is what we see here, the scale here. So our highly prioritized areas that we want to look at is areas where there are very low tree diversity, so a loss of big trees, but at the same time, high shrub diversity, so higher increase in shrubby encroachment. So this is essentially these blue shaded areas. And now we know which areas that we have seen shifts in, we need to prioritize for management. And here we can tell management, okay, they need to go to these specific blocks first to prioritize resources for clearing shrubs as well as preserving trees. Then we go on to our next ecosystem, the fynbos. And here I focused on degradation, legacies, drought, and how this affects ecosystem stability in the fynbos. So the fynbos, for some context, is a very hyper-diverse ecosystem. It's only found in the southern tip of Africa, and this small area hosts more than 9,000 species of plants, of which 2/3 are found nowhere else in the world. So just to give a bit more context for how diverse it is, it hosts 3% of the world's plants and less than 0.05% of the Earth's surface. So a very special area. Unfortunately, the hyper-diverse fynbos is also threatened by various different change drivers like climate change and anthropogenic degradation. In our case, we're looking specifically at exotic plantations. So this is a photo taken near my home in South Africa, where we have indigenous fynbos vegetation alongside exotic plantations. So these plantations were originally established decades ago by settlers for windbreaks and timber production. And although they have several benefits and ecosystem services, the problem occurs when they consist of invasive alien species. And this is unfortunately the case with many of the plantations in the fynbos biome itself, as they consist of pine and eucalyptus species that are non-native and invasive to the native indigenous fynbos vegetation. So the challenges that these exotic plantations bring is that firstly, they drastically reduce water runoff because they're quite thirsty, which affects water supply. Additionally, they are more flammable than indigenous fynbos vegetation, because fynbos is a very fire-dependent ecosystem that heavily relies on fire for its ecology. If we have suddenly hotter and longer fires, this can significantly disrupt ecological processes. Then they also impact native soil, seed bank, and properties, which later impacts biodiversity. And then lastly, even after these plantations are cleared, these areas are often more vulnerable to re-invasion by invasive species. And these species can outcompete native vegetation for resources. So in this study, we focused on the last two. So soil, seed bank, and the re-invasion. And in this case, we classify their effects as degradation legacy effects. So legacy effects are defined as long-lasting impacts of past disturbances and activities, which in this case means that past plantations that have already been cleared still have lasting impacts on restored ecosystems in the present day via the fact that they had an impact on the soil, seed bank, and they allow for more presence of invasives. So, and this in turn also influences how ecosystems will respond to climate change and other natural disturbances. So what are we trying to then figure out in this study? We specifically want to disentangle what the effects of exotic plantations in the past are, and we want to on the ecosystem in present day. And we want to see what these direct effects are on biodiversity and what these indirect effects are on stability of the ecosystem during drought. So we will be specifically focusing on biodiversity and stability going forward. So to assess the first thing, biodiversity, we did a biodiversity analysis, which involved some fieldwork in the Steenbras Nature Reserve. Here we have the study area. You can see it laid out. And these different colored dots are where we did our field campaigns, where we measured biodiversity. And we essentially wanted to compare natural areas that have not been impacted by plantation in the past versus degraded areas that have. So the degraded areas are colored in red and orange. Red means that the plantation that was there in the past lasted longer than 30 years, whereas orange means it was up to 30 years, the plantation in the past. And then these areas with no coloring are just areas that never had any impact from plantation. So we basically compared degraded areas versus natural areas. Here you can see some photos already from the field sites. So on the left, we have a natural area. On the right, we have a degraded area. And something to note already is that in the natural field plot, we have a bit more variation. So there's a lot of different species, a lot of different flowers. You can see it's not as uniform. Versus in the degraded area, it seems that it's mainly one type of plant that dominates the majority of the area. So based on our actual statistical results, we found the same. We found that the degraded areas had lower overall species diversity, as well as they had more weedy species and more alien species. We also found that these results are if these effects become even stronger, the longer the plantation was there in the past. So the longer the duration, the lower the overall species diversity and the more weedy and alien species there are. Then we move on to the next step, so looking at the stability analysis. And here again, we incorporated remote sensing in a combination with a spatio-temporal hierarchical Bayesian model. Quite a mouthful. But basically, what this model does is it tells us how we would expect healthy fynbos vegetation would respond to fire and during drought. So it incorporates a bunch of input variables, for example, a remote sensing time series of vegetation throughout time, fire data to tell us when a fire occurred at each location, as well as some ecosystem characteristics, so the soil type, the terrain, and the vegetation type. And based on this information, it can plot for each location what it would expect the healthy vegetation to be like. Then we can use this to compare our stability in terms of natural areas as well as degraded areas. And then we compare it based on two stability metrics. Firstly, post-fire recovery. This is important in fynbos because how quickly the ecosystem responds after fire can tell us a lot about how healthy it is. And then we also look at temporal drought stability. So how well does it handle the stress driven by drought? So this is the output for one location from that model. And what you're looking at here in red is basically what we measured with remote sensing is the change in vegetation through time. So this is what is actually observed by the satellite and what is happening in the field. Then the model predicts what it expects the healthy vegetation would look like. And this is these bands, these dark and light gray bands. So this is what it expects how the vegetation would vary. So post-fire recovery in this case is basically if a fire occurred here, which we can see that with the sudden dip, it tells us, we look here at how quickly is the vegetation recovering after the fire. So basically the rate of this increase here. Then the temporal drought stability is we look at what is the observed vegetation response versus what the model expects for healthy vegetation. And essentially the bigger this arrow gap here is, the more the actual vegetation deviates from what is expected for healthy vegetation, and thus the more unstable that specific location is. So what did we find? So now again, we're comparing post-fire recovery and temporal drought stability for natural areas and degraded areas. And what our final results showed is that natural areas where no plantation occurred in the past, the vegetation recovered slower after fire, but was more stable during drought. So the drought effects had caused less stress. The opposite was true for degraded areas, however, which showed a very fast recovery after fire, but the vegetation experienced much more stress and was much more unstable during drought. And then again, similar to what we saw in our biodiversity analysis, we once again found that these effects were stronger with a longer plantation duration. So to summarize this all together, based on a previous graph figure that I showed you, basically what we saw here is that past plantations have an effect on biodiversity that it lowers overall biodiversity, and it also increases weedy and invasive species. Because of this, it indirectly affects post-fire recovery and stability, firstly by making post-fire recovery faster, but also by making the ecosystem more unstable during drought. And what we also found is that the longer this plantation in the past, the more severe these effects are on biodiversity and stability. And again, if we try and bring this back to management implications, if the goal is to eventually clear a plantation and restore it to natural indigenous vegetation, it is important to do the clearing sooner rather than later so that we can avoid an ecosystem that struggles too much under drought. So to conclude, basically what this research shows us is that from fynbos to savanna, so various different ecosystems. Remote sensing is quite a robust and vital tool for monitoring and managing rural ecosystems, especially if we can combine it with local biodiversity data. That is the end of my talk.
Okay, should I start, or are we gonna do should I start?
Yes, you can start.
Okay, let me share my screen. Can you see my screen?
Yes.
Yes.
All right. Thank you, everybody. I am Shiridzi. I'm gonna be sharing my second chapter from my PhD, which is titled Optimizing Local Climate Zone Through Clustering for Surface Urban Heat Island Analysis, a case study of Capetown. Before I even start and go on, let me announce I'm a person who status. So if I stumble a little bit, it's not your internet connection. It's coming from my side. But anyway, let me start. Before everything, I'm going to introduce you to what the main concept is, which is the urban heat island. This is a phenomenon where urban areas experience higher temperatures compared to the surrounding rural areas. It is caused by urban activities and the urban landscape, which includes artificial surfaces and infrastructure. So we are looking at things like your industrial zones. We are looking at the population. We are looking at the traffic, and then we are looking at the urban infrastructure itself. So the results of this urban heat island is that it results in environmental, social, health, and economic distress. So it can be divided into two components. You have the atmospheric component, which can be called the air urban heat island, which is affected by more variables, and it's much more harder to study. And then you have the surface component, which is called the SOHI, which is what we are going to be focusing on for this chapter. This is much more easier to study in that we can employ remote sensing to study it through land surface temperatures. So the main framework that we are going to consider for this chapter is called the local climate zones. This is a universally accepted framework that was developed particularly to study urban heat islands. It consists of 10 built and then 7 natural classes. So the local climate zone framework was established on the premise that all these classes are supposed to be thermally distinct universally for both the atmospheric and then surface component of the urban heat island. But the challenge comes in that some of these classes, they share great physical similarity, which the typology does not account for. Secondly, urban areas have different morphology. For example, how a compact low-rise appears in Capetown is not necessarily how it is going appear, how it is going to appear in East London. So then this brings us to a few research questions where we asked ourselves, to what extent are these similarities propagated onto the surface temperature patterns? Then secondly, we had to ask ourselves, are these individual classes thermally distinct enough for practical applications? After that, then we asked, can the framework be optimized or in a way clustered for practical applications, which led us to the aim of this chapter, which was to develop a SUHI optimized version of the local climate zone framework that will have practical applications. So I'm just going to run you through the methodological framework. I'm not going to go into detail, but I will touch the most important aspects of it. So we start with Landsat remotely sensed images, from which we then classified the local climate zones using random forests, and then on the other hand, we extract the land surface temperatures using a single channel algorithm of the inversion of Planck's function. And then after that, we do an overlaying of the local climate zones with the LST, and then extract the values with a 100-meter point grid. On the one side, after that, we do a graphical analysis of the trends between the local climate zone and the land surface temperatures. And then on the other hand, we do a statistical analysis where we start with an ANOVA, and then after that we do a Tekis post hoc test, and then we put that through a hierarchical clustering algorithms. I'm just going to jump into the results immediately. So from the land surface temperatures versus local climate zones, if you compare the two, there are some things that we can immediately see from that. Follow me as I take you through across some areas. There on the first box, we are looking at the harbor area in Cape Town, which is predominantly local climate zone 8, which is the large build. And then you see that the corresponding land surface temperature shows high temperatures. Then the second box zooms in on the Table Mountain area. At the Table Mountain area, you can see that the LST shows lower temperatures. Then we go through the agricultural lens of an area called Philippi, where you see the land surface temperatures showing a mix of low temperatures with some moderate temperatures. Then we look at the area that is mostly dominated by the informal settlements. So where the informal settlements are, you find that the temperatures are higher, but where you have some vegetation, then the temperatures are lower. But this is just a visual analysis of the patterns that stand out. For the rest of the area, the patterns are not really clear. They don't really stand out. So we can't really make conclusions based on the visual assessment on itself. So secondly, we look at the mean LST values per class. And what you can already see is that the highly impervious classes, which is local climate zone 8, which is the large build, and then 2, it's compact mid-rise, and then 7, which is your informal settlements, and then 3, which is your compact low rise. They appear to have the highest mean surface temperatures. And then you see that the vegetated classes, which is local climate zone 14, 11 and 13 have lower surface temperatures. But when you consider the water class, you're finding that it has the lowest surface temperature across the board. But the other thing that you can also see here is that the summer and the spring, they have a much wider variability than you find in the winter and the autumn. But for me, the most important thing to check here is that even in the spring and the summer months where you have quite a large variability, you still find classes that have means that are almost the same. If you look here where we zoom in on local climate zone 2 and 3, the mean of 2 is about 36.9, and then the mean of 3 is about 37.1. So the difference is about somewhere between 0.1 and 0.2. But the challenge is that a difference of 0.2 does not have practical applications. It is basically the same, and you see the same thing happening with local climate zone 5 and 6. You see the same thing happen with local climate zone 9 and 14, where the means are almost the same. But again, this is just a graphical assessment. We can't make statistical conclusions based on just this. So then we move to the statistical part, where we have to somehow separate between statistical significance and practical significance. When we talk about statistical significance, the only thing that it tells us is that a difference did not occur by chance. So the challenge in this regard is that the difference can be astronomically small, too small to have a real life effect, like we just saw with local climate zone 2 and 3, where you had a difference of about 0.1, which does not really translate into the real world where it's going to have a real life effect. So the solution to that was that we adopted a practical significant threshold of 1 degree. This is based on ecological processes and previous research. So we then put our points, our sampled points through ANOVA, and then through a post hoc test after. So I'm gonna show you the results. This is the result after we put it through the post hoc test. And on the one in the far left, the one in the far left with the red dots shows you pairs that are not statistically significant, which means that the difference between the means could have occurred by chance. And interestingly, the same pairs that are considered not statistically significant are the same pairs that we observed when we looked at the graphs. You see 14 and 9, you see 2 and 3. So the same classes that we observed. However, when we introduce a 1 degree threshold, we are finding that more pairs pop up. So these are pairs that might not belong to the same parent cluster like 2 and 3 do, but yet they have similar thermal environments. The same as like, for example, 7 and 3, which do not really appear in the same parent cluster but have the similar thermal environments. And so having highlighted so many pairs that do not meet the 1 degree practical threshold, we introduced clustering algorithms, where the first one was a semi-automated algorithm, which is an agglomerative clustering algorithm. It's a purely spectral approach in that it groups this local climate zone based on the similarities in their physical characteristics alone. It relies on an input matrix that looks like this, where we had 4 fields there. We had the first field, which is the density. Then we had vegetation cover. We had height. Then we had impervious surfaces, where we ranked them from low to high. And then we put that inside the semi-automated algorithm, and the result looked something like this, where based on the physical appearance alone, it grouped 9 and 14 together. This is the low vegetation and the sparsely built. It grouped them together, and then it grouped 7 and 10 together. These are classes that appear more industrial in their appearance. It grouped 2, 3, and 8 together. These are classes that are mostly impervious. And then it grouped 11 and 13 together. And then 17 was on its own, and then 5, 6, and 16, which were the open classes, were put together. After this, we did a fully automated clustering algorithm, which is more of a divisive hierarchical clustering. Instead of using the physical appearance, it uses the values of the land surface temperature itself to cluster them. So it uses 26 built-in indices to determine the optimal number of clusters. And then after that, it uses Watt's method to assign LST points to each cluster. So the results looked something like this. This fully automated algorithm grouped 9 and 14 together, just like the one that is based on physical appearance alone did. It grouped 2, 3, and 8 together. It grouped 5, 6, and 16 together. Then 17 was still an independent class on its own. The only difference here is that instead of grouping 13 and 11 as one cluster, it separated them. And then instead of having a cluster of 7 and 10, it separated them, where 10 was put in the mostly previous class, and then 7 was assigned with the more open clusters. Then we put it through another round of the cluster practical significance analysis, which is another round of Turkey's postdoc test. And I'm just going to bring those back so you can follow up on what the clusters contain, what they look like. And even from there, you can already tell that the clusters that are associated with sorry, the pairs that are associated with cluster 5, which is the water bodies, they have a great difference in that it does not seem to appear to look like any other cluster. So the temperature disparities are much more wider. The same can be considered, the same can be seen for vegetation as well. But the interesting thing comes in when we look at the built classes, where you are finding that as much as the differences is not large, it is still above the practical threshold, the practical significance threshold, which was 1 degree Celsius. So I have a few examples of how to practically apply this in the Q&A. You can ask if you're interested, but then I'm going to move to the conclusions, where we conclude that the similarities in the local climate zone physical characteristics are indeed propagated onto the land surface patterns. And the solution is that a cluster typology is the only way to achieve practical distinct thermal environments, where we move from a 17 class typology to a 6 cluster typology that best describes the surface thermal environment. The paper was published. Thank you.
Thank you much. Thank you very much for the presentation. Also to Lisa. Bruno, would you like to share your part as well?
Okay, yeah, thanks, Laura. Then I'll share mine just for like 2 minutes. It's in fact a concluding presentation. It's okay. Does that work? Can you see that now?
Yes, perfect.
Okay, right. So in the former 2 presentations, that's actually, you could say this could have been an entry slide, but I was planning to use a bit of rubber time at the end. So we start with the full content, and the 2 presentations of both Liesel and Chirizi, they give you an example of what can be done with remote sensing, both for the urban and rural development. And this is actually the result of the project. So you could also see this project was actually like a last sprout of the former CLIMOS network that was looking at climate change and development aid. So this was actually work of 4 partner universities. You can all see them here. They were all involved. Okay, people presenting right now are mainly from KU Leuven, although Chirizi has a past at Univen before joining KU Leuven. And well, we had a close collaboration with the SAF-ADAPT project, which is actually a short word for the South Africa Flanders Climate Adaptation Research and Training Partnership. And I'll actually give you the website there if you want to find more information on that. And the 2 partners in Venda and also in Fort Hare, they also had like risk and vulnerability science centers, and that's also where quite some training was given and collaboration was actually going on. They have more like a provincial mandate within South Africa to tackle climate change. And through that SAF-ADAPT project, where we had like a very close collaboration, you had the Department of Forestry, Fisheries and the Environment, which is actually hosting the climate adaptation unit within the South African government. And through UCT, we had a direct link with some of the outputs of both projects, where Resider was taking care most of the remote sensing results. And DEF was also hosting that adaptation network, and that is still operational, and that should lead South Africa through the future years of climate change adaptation. And in the margin, I also like to mention we had a short stint with VVOB, a Flemish parastatal that's actually working more on climate education for climate change at secondary schools, and that's also where we had like students working. And you can see this effect a short list. You've seen the ones in yellow. You saw the first 2 ones actually presenting. They were sponsored by the Resider project, but through the SAF-ADAPT we could send a pretty large group of students to South Africa. I think some of them are actually attending this session, all tackling different topics of where research is required and capacity building is required, problems that South Africa is trying to solve now in the coming years. You can find more information on those 2 websites, both the SAF-ADAPT website and of course also the KU Leuven website. And with that, I would like to conclude. Back to you, Laura.
Yeah, thank you very much for this conclusion or textualization. And also, of course, thanks to Chirizi and Liesel for your presentation. We would like to open the floor for the audience to ask questions. Was something unclear? Do you want to share your own experience? If so, please unmute yourself, put the camera on, and feel free to ask your question directly to the speakers. in our experience, it's always a bit tricky to be the first one. So if okay, I had a small question myself. It's a bit related to what you said at the end, Bruno. So I see that the research is somehow really embedded in the policy making at the policy making level. Can you share a bit more on that? Also, if the PhD projects were directly linked to policymakers, and how did you set that up? Was it easy? Because we know that it's not always convenient to translate policy or research output into policy. So how did you do that? Was it convenient? Were there some challenges you faced?
Yeah, it was actually a bit well, demand driven. So DEF, the Department of Environment and Fisheries, had a close collaboration with the ACDI, which is based at UCT, which is also there the climate change unit. And Mark New there, who is leading that unit, or who was leading that unit, is actually having, well, a national voice in what South Africa should do climate adaptation wise. And yeah, he was also involved with the Flemish government, and through that, then the Klimos network got also involved, and that's how Resider and both SAF-ADAPT actually got established. And then, yeah, we were discussing a bit, okay, what can we do from the KU Leuven side? Because it is not always that practical. We are a bit far away from South Africa. So there was actually a bit of task sharing with the wider agenda, with a lot of field work was mainly done by the partners at our South African partners, and KU Leuven took more charge of the remote sensing work. Of course, also coupled with field work, a bit what you saw in the former two presentations. But because there was actually an existing discussion between scientists from ACDI and the policy world, it was actually quite easy for us to step in, actually. So we didn't have to invest time in that. That is why we could invest more time in the research itself, because it was already established. That was actually a very pleasant way of working.
Yeah, thank you. Very interesting to hear. I think also for people working in another field, very interesting to make use of the same or a similar approach. Is there another question from the audience? Mr. Gert Verreet, please take the floor.
Yes, very interesting. Thank you for the presentations and the enlightenment. Following up, I'm Gert Verreet. I work for the Flanders Department of Work, Economy, Science, Innovation and Social Economy. I'm a science policy advisor on natural sciences. And following up on the question from Laura, I mean, these are one-off projects as PhDs, but do you see any uptake that some of the tools developed and some of the, basically the observing capacities and so on, that they become more streamlined in operational work by agencies and so on? I'm also involved in the stereo program at Belspo, and so we try to also push, of course, applications of remote sensing and so on. Is there any uptake from regular data provision from those systems that are in place, like from Copernicus or whatever sources?
Well, we were trying to use them. I'm not so sure about the policymaker side, actually, but a lot of the content, so within that SAF-ADAPT project, we also had like yearly training workshops for all the students involved, both PhD and masters. There's another long list of master students that I did not show. That was part of that larger SAF-ADAPT project, and they all attended there. So there we had like training workshops of 20 to 30 people attending. That was in fact the fixed group, so to say, but also with sometimes a higher daily occurrence because it took place at these partner universities. So I think at the university level, that's where I think the capacity got strengthened. Also, the unit which Ritzi came from, well, they were already using remote sensing. And I think the package that they have now got actually expanded through this project. So there are clearly points and places in South Africa where they are using it. And I think we contributed to that, to what was already existing. To what extent it is taken up by government services doing all that image processing themselves, I'm not so much clear. So maybe that's a question for Lisa or Chilidze if they know more on that. It could also be that it's in the university world, and then that they then serve the policymakers. But maybe that's a question for Lisa or Chilidze. Maybe you want to add on that from Chilidze, and then Lisa, from the South African side.
From my side, we were contacted based on the first chapter that I did, where we classified Cape Town and East London and Thohoyandou into local climate zones, and then we were contacted by the South Africa Medical Research Council. Bruno, remember Thandi? So so they were interested in having to use the same classification approach that we did. So I guess that would count as an independent research institution that has taken up the approach that we developed in classifying local climate zones.
Thanks, Luigi. That's very correct. Actually, Carol Mewa-Fotso is actually, I see now her name on the list. I was actually the last student that joined this project to actually go to South Africa to see to what extent indeed. So there was a clear demand from SAMREC, the medical health service, to see to what extent these local climate zones actually have an impact. And Carol was actually collecting health data and is now carrying out research to find correlations between heat-related diseases and these local climate zones. Right. Okay. Over to you, Liesel.
Sorry to interfere, but I think there is a similar project for West Africa funded under, if I'm not mistaken, funded under Stereo. So something about heat related in megacities in West Africa. I don't know exact reference, but somewhere in my mind is still a legacy of.
Okay, thanks for the tip. I was not aware, but we will look it up. Yeah.
In terms of the rural ecosystem effects, South Africa has quite an extensive network of national parks. It's a very big country with a lot of nature. And these it's called SANParks, the bigger organization that governs it. And they are already very interested in remote sensing. And through my fieldwork, I came into contact with quite a few people because I had to do fieldwork in a few different sites. And through that, they also became interested in how they can kind of use these workflows that I explored in my chapters to inform their decision making. So I don't know if that's really policy, but more from a management perspective, maybe that they can later start deciding on policy decisions regarding how they manage fire, how they manage herbivory in the savannas, these types of things. So yeah, there are talks of how to incorporate these types of analysis to inform their decision making, because up until this point, until I met them and had a meeting with them, they had been using more just their own knowledge and literature to try and figure out in different climate change scenarios, what would we expect would happen. But now we have some data-driven results that we can use to help them kind of either say, okay, yes, this is clearly this type of area is going to experience an abrupt shift if there are more severe rainfall. Now they have some concrete proof of, yes, this is the type of thing that would happen, that they can feed into their workflow and their workshops. So it's very welcomed at least in terms of monitoring ecosystem stability in South Africa.
All right, very interesting. Thank you all for your answers. Maybe it might be useful if I put you all in contact for further exchange with Gert to see if it's useful to inform each other a bit more on possible overlap or synergies. But thank you for that already. I see we come at the end of this hour. Are there still some questions in the audience? If so, then please go ahead. Check.
If I may interrupt, I would like just to make an announcement. So we are also supporting some UNESCO-related projects in Southern Africa, and if you would have an interest in having a look, one of them deals with Kruger Park also, and one is called it's more on landscape management with involving local stakeholders, citizen science related issues and so on. If you have an interest, the speakers, I would gladly forward the project documents after this meeting. Just for your information, there will be a kickoff meeting of that UNESCO project on the 26th of March online, and I will send you the details of that as well. So thank you.
Great. We look forward to that.
Yeah, also very happy to see this exchange happening. All right, thank you all. I'm afraid it's time to close off. So thank you everyone for attending this community talk. We appreciate your attention and participation. As we just saw, sharing experience and insights are very valuable. So we are grateful for your contribution. And of course, special thanks to our speaker, Lisa Vermeulen, Tishelti Magnagna, and Bruno Verbist for your presentation and discussion. I personally learned a lot. I'm sure the audience did too. Liesel and Tishelti, as you are at the final stage of your PhD, we wish you all the best in completing and defending your PhD. And then looking ahead, we are excited to invite you to the next community talk. We will be a bit a special edition, as March marks the 5th anniversary commemoration of the start of the COVID pandemic. We will host presentation and discussions on various related global studies related to infectious diseases. This will take place on Wednesday, March 19th from 10 till 12. So instead of 11, it will start 1 hour earlier. So warmly welcomed to join next month. Stay tuned, follow our website and social media platforms for updates. We wish you a lovely day and we hope to see you all in March. Goodbye.